Hi everyone, I'm Matthew. I'm a postdoc at the University of Auckland, and today I'll be speaking about a Schottky lemma on N generators for cat0 spaces. And this is joint work with my colleague Jeroen, who's also at the University of Auckland. So generally speaking, a Schottky lemma is a combination theorem. So it gives set theoretic conditions under which elements of a group acting on some set generate a free subgroup. And there's many different versions of these lemmas, sometimes called Schottky lemmas or Klein combination theorems, or even the ping pong lemma, many different versions of them. And so a well-known example is the Sarnov subgroup. So you take this two-generated subgroup of the group SL2Z, generated by these two matrices here. The group SL2Z acts by Mobius transformations on the Riemann sphere. And these two matrices act on the sphere in such a way that essentially one of them shifts the bottom half of the sphere here to the top, and the other one does the opposite action. So this is where the name sort of ping pong lemma comes from, and that these two matrices are almost playing a game of ping pong on the Riemann sphere. So they satisfy these certain conditions, and so these two matrices generate a free group. So in a paper I wrote in 2020, coming out of my PhD thesis, I gave an algorithm which used a specific version of a Schottky lemma to decide whether a two-generated subgroup of the group SL2QP, where QP is the p-adic numbers, is both discrete and free. So by discrete, I mean every subset is open with respect to some topology, and the topology we're taking on this group is just the standard one. You embed each matrix into QP to the 4. So the version of the Schottky lemma which I used for this algorithm uses the action of this group on the corresponding Brouhart-Tietz tree. And so this is a theorem of Lobotsky, so it's a version of the Schottky lemma for groups acting on trees. So if you take n hyperbolic isometries, G1 up to Gn of a simplicial tree T, you denote their axes by gamma 1 up to gamma n. If for each of these elements, there's an open segment of length equal to the translation length, which I'll denote L of Gi, and this open segment is contained inside the axis gamma I, which satisfies the following property, that the projection of every other axis gamma j onto this gamma I, so there's just a geodesic projection, is contained inside this open segment of length, the translation length of Gi. So if all n of these elements satisfy this condition, then they generate a free subgroup of the isometry group of this simplicial tree T. Furthermore, if this tree is locally finite, so every vertex has a finite number of neighbors, then the subgroup you get is also discrete with respect to the topology of pointwise convergence, which is a standard topology that you would take on the isometry group. It's equivalent to the compact open topology if you're familiar with that. Okay, so current research I'm doing is trying to extend this algorithm from two generated subgroups of SL2QP to 3 or more generated subgroups of SL2QP. So this this version of the Schottky lemma by Lobotsky applies for n hyperbolic isometries. So in theory, it should be possible to develop such an algorithm, but it's becoming quite tricky to sort of, in practice, given n matrices, how do you determine how their axes interact? Anyway, the motivation for this talk is that you might want to generalize to sort of finitely generated subgroups of SL2QP with a high number of generators, or we could try and generalize the dimension of the group. So we could look at finitely generated subgroups of SLNQP and try and identify discrete and free subgroups of that. This makes things a bit more tricky because SLNQP for n at least 2, these groups act on a Brouhart-Tietz building, which is for n being 3 or more, is a much more complicated geometric structure than a tree. And so sort of motivated by this question, my colleague Jeroen and I proved the following version of a Schottky lemma, which works generally for for isometries of any cat zero space X. So if we take n hyperbolic isometries G1 up to Gn of this cat zero space X, again, the axes are denoted by gamma 1 up to gamma n, and we suppose this additional condition. So for every pair of axes, gamma I and gamma j, either they intersect in a bounded segment, and then we insist that the angles that the endpoints of the segment make between the axes gamma I and gamma j are both pi, or the axes gamma I and gamma j are disjoint, then there's a geodesic between them, and we insist that all 4 angles made between this geodesic and the 2 axes are all equal to pi as well. So if every pair of axes satisfies these conditions, and we also have the same projection condition as before, so every axis contains an open segment of length equal to the translation length of the corresponding element, which contains all the projections of the other axes onto that axis, then the subgroup of the isometry group of this cat zero space X generated by these n elements is free of rank n. And then in this case, if we additionally suppose that X is locally compact, then this subgroup of the isometry group we get is also discrete with respect to the topology of pointwise convergence. So essentially, this is almost a direct generalization of the Schottky lemma given by Lebotsky, but it now applies for any cat zero space under these additional assumptions. A similar version of this was proved in a paper written in 2002 by Alperin, Farb and Noskov, but they focused on the case where n equals 2, so you're taking a pair of hyperbolic isometries, and they had additional assumptions that X was a complete cat zero space with no fake zero angles. So this version of a Schottky lemma for cat zero spaces that Jeroen and I have proved is very, very general, and it will certainly work for our purposes where we wish to investigate finitely generated subgroups of SLNQP acting on Brouwer-Tietz building. Thank you very much for your time. Cheers.